All right, folks, so we are on the back page of our note packet, and we are starting the last part of this unit with piecewise functions. The first thing that I want you to know is that word piecewise kind of tells you what the function is going to involve. Piecewise functions are one equation and multiple pieces. So one equation, one function, but multiple pieces to it. And it's written using two or more expressions. So folks, looking down at number 1, we've got f of x equals 2x plus 1 if x is less than 1, and f of x equals negative 3x if x is greater than or equal to 1. Oftentimes these are drawn with kind of a squiggle bracket in front of the equation parts, so that we see that f of x is equal to these two linear functions. So f of x can be equal to 2x plus 1, or f of x can be equal to negative 3x. And folks, we're going to go ahead and write those pieces to the right of it. F of x equals 2x plus 1, and then f of x equals negative 3x. So this is all one equation, but we write it as two separate pieces when we are trying to graph it. So one equation, multiple pieces. The other thing that I want you to take away from piecewise functions is that by definition, these are functions. What do you guys remember about functions? They need to pass the vertical line test, pass the VLT, and that also means no domain doubles, no x values getting used twice. Keeping that idea in mind that these are supposed to be functions is a good thing to keep track of as you are checking yourself. So kind of like we have that line of reflection to make sure our graph of the function and its inverse looks accurate, knowing that these should be functions will be a good way to check yourself. So a piecewise defined function, it must pass the vertical line test, and it's written using two or more expressions. We also have step functions. We're not going to get into these today. This will be next week. But they are piecewise constant functions that increase abruptly from one constant value to another value. So I just want to show you an example of a step function. So let's say I have this closed dot going to this open dot. It's a constant horizontal line. I'm defined at this value, this value, this value, this value. And as soon as I hit that open dot, I stop being those values and I start being these values. And then I have another step. The open dot and closed dot represents where I stop being this piece and start being the other piece. And then it continues up the graph as such. And they will look like little steps. So a step function is an example of a piecewise function. And I want to go back to that vertical line test for a moment. If I put a vertical line, how many places are we hitting the graph? Only once. So what's going on with that little open dot then? Our function isn't defined there, but it has to be there to show, kind of as a placeholder, to show that that's where it stops being this function and starts being the other function. So the open dot itself does not count as an actual point because your function isn't defined there. So this crazy little thing does pass the vertical line test, and it is a function. As far as buy-in goes on this, how many of you have ever had to take a car in for repairs? Or have ever been to a hairdresser before? Step functions and piecewise functions actually come into play with both of those. So I want to show you an example here. So a lot of times I'll take my car into Firestone and I go in for an oil change, and then it ends up being, a couple $1,000s, no big deal. So Firestone, we'll say they open at 8 a.m. When I walk into Firestone, am I paying any money for repairs at that point? No. I've got an open dot here at, we'll say, $15 an hour. So at the point at 8 a.m. when I walk in there, I am not paying anything. But as soon as they start working on my car, I immediately start paying an hourly amount. And this is not even including like machine parts and costs like that. So this is just like hourly wages. And so let's say they work on my car all day. But at 8 p.m. when Firestone closes, what happens? Are they going to keep working through the night? No. So at 8 p.m., I stop paying that hourly amount and I start paying a constant rate. So maybe I have to pay an overnight fee so that they have insurance on like their parking lot or something. So in order for me to have my car there overnight, maybe I have to pay this little flat rate, like I pay $5 more. And that continues until 8 a.m. the next day. And see, I have this open dot and closed dot on the same spot where I stop being this constant function and I start being the hourly rate again. So sometimes this goes into programming, figuring out how much your bill is going to be for a place like this. Hairdresser, it's like you go in for a standard cut, it might be a flat rate. But then if you go on for a hair dye, depending on how much hair you have, then you might start paying a gradual increase more based on what the hairdresser actually has to do. So there's a lot of different like cost applications of piecewise functions that are related to kind of a flat rate or hourly rate out in the real world. So looking at this function, I'm going to draw in a dashed line here and a dashed line here. Find when we graph these functions is that these are called bound lines. And they divide up my graph into different sections where I have different function pieces. So if I were to write the equation of this piecewise function, it would be more like this one over here where I have 1, 2, 3 separate pieces, 1, 2, 3 separate pieces. The bound lines show me what the function parts are doing and where it stops being one function and starts being another function. Also notice that each piece goes from start to bound line to bound line. Those bound line values are included even though this function isn't even defined on that line. It's got that open dot there as a placeholder. So a lot of times I like to start with what the graph looks like because I think that's sort of helpful when we go into making our own graph from the equation. So folks, we've got these lovely set of steps for us. You do not have to memorize them word for word. By any means, I never be like, please recite the steps for doing a piecewise function. But I do expect that you know how to apply these steps to the actual graph. So step 1 is to draw the boundary lines. The boundary lines come from the bound statements. That's these if statements with inequalities that are to the side of my function pieces. So I've got f of x equals 2x plus 1 if x is less than 1. F of x is negative 3 if x is greater than or equal to 1. Those if statements are going to tell me everything I need to know about the bounds. So I look at the number parts of the bound statements and I see that I have a value of 1. This tells me we are going to draw a bound line at 1. So those values in the inequalities become the bound line. And this has broken my graph into 2 areas. 1 for the pink function, 1 for the blue function. If you're like, how do you know that this one's going to be for the pink function, Mrs. Cairo? This if statement tells me where this piecewise function is defined as this one. It says if my x values are less than 1. If this is 1, where are my x values less than 1? To the left or to the right of that line? To the left. So x is less than 1 over here. And then if I look at the other bound statement, it says x is greater than or equal to 1. And you won't have to do that on every graph. We're just showing that that's what those bound statements mean. And that's how it is, dividing the graph up into 2 areas. So step 1, draw the bound lines. Hooray, we're done. Step 2, make X, Y tables using the boundary values. And I want you to add something to this. It says using the boundary values and the inequality statements. For other 2 points. So use the bound values and inequality statements for the other 2 points. So we're going to make XY tables, one for each function piece. This pink one is going to get an XY table, and this blue one's going to get an XY table. So both of these tables are going to start with the bound value, which is 1 for the pink line and 1 for the blue line. We use the inequalities to determine open, closed at the bound value. If this top function is defined for x values less than 1, can I really choose 1 as an input? Is 1 less than 1? It's not. So I have to still use the bound value, but this whole, this one's only defined for x values less than 1 tells me that I am going to have an open dot for that point. Looking at this bound statement, it says if x is greater than or equal to 1. That means that this one, we will have a closed dot. Okay, let's go through those steps one more time. How did we know this was a piecewise function? Because it looks awful, Mrs. Cairo, because there are multiple linear pieces to it with one function notation, and we've got these if statements and inequalities, bound statements. So that's how we knew this was a piecewise function. Next, we looked at those if statements, the bound statements, and we decided that 1 was going to be where our function is splitting. That is the line where our x values are splitting into 2 areas. We use that value as the starting point in both of those tables. If it's less than or greater than, open dot. Greater than or equal to or less than or equal to, that's going to be a closed dot. And now we use the inequality statements for the other 2 points. So this pink one says x values less than 1. What's something less than 1? 0. Nice and easy. We love it. What's something else that's less than 1? Because we need 3 points in our table. -1. Keep them small. Keep them small. So then what about blue table? Here we want x values that are greater than or equal to 1. So how about 2? How about 3? To me, that's the toughest part of these problems, is figuring out what you're going to choose for x values in the table. And just to pull back for a moment, all the other equations we've seen before in this chapter, it's like, yeah, we've got our transformation rules, that's all good, but also we've normally been able to make input-output tables for stuff. This is restricted on what I can plug in for x. I can't plug in 5 because that's not going to be this function piece. I can't plug in -3 here because that won't be on that function piece. Those bound statements restrict us on what we can actually plug in for an input. And now that we have those inputs, now we plug them into the equation. So 2 times the x value of 1 is 2 plus 1, 3. 2 times 0 is 0 plus 1 is 1. 2 times -1 is -2 plus 1 is -1. And let's plot those points. Forward 1, up 3. Hey, make it a big open dot because I'm old and I don't want to have to guess whether it's a tiny open dot or not. So make those open dots nice and big for Mrs. Cairo. So there's 1, 3, an open dot. 0, 1, a regular dot. -1, -1, another regular dot. Ooh. Is this line going to have arrows on both sides? Going off in this direction feels right, because it's like, yeah, that's where my x values are less than 1, going that way. If I start going this way in the opposite direction that my points are going, I'm going to be getting into that other function pieces territory, which we do not want to do. So on piecewise functions, sometimes you'll only have one arrow, and sometimes you might not have any arrows at all. So more on that later. Let's go ahead and plug in our other inputs for our other function piece. -3 times 1 is -3. -3 times the x value of 2 is -6. -3 times the x value of 3 is -9. And now we plot these points. Forward 1, down 3. That closed dot, it's just a regular dot. We just kind of designate that open close business so that we don't have two closed dots stacked on each other. Forward 2, down 6. Forward 3, down 9. Are we going to have this arrow going up into the left or down into the right? Down into the right. Whew. And now I see I have two function pieces for this one piecewise function. So as I read this graph from left to right, it's my pink line, it's my pink line, it's my pink line for all inputs that are less than 1. When I hit 1, is it my pink line anymore? Nope. Then it pops down and becomes my blue line, going down, going down, going down. We're not going to do anything with this, but I want you to think about it. So this is not something that you're going to be tested on or anything, but I want you to think about it. What is the domain for this function? Or maybe we should ask, is it a function? Does this pass the vertical line test? Yep, because if I put 1 here, that open dot saves me because it's only hitting in one spot. So it passes the VLT. That's my check saying it's all good. I have done the problem correctly. But what about the domain? With the people sitting around you, I want you to see if you can determine what x values are covered from left to right. Go.
Sounds like programming.
Very much so. Yeah, piecewise functions are very like, so we got this for this condition, this for that condition. Very much programming. Does anybody want to guess? It's easier than you think. In fact, there are no inequality signs in this. It is all real numbers. Did anybody else guess that? It's confusing though, because it's like, hold up. The graph is fragmented, like there's two different pieces. So how is my domain just all good from left to right? I'm going to show you. So we start over here at the far left. These values are going all the way down. So here at -infinity, yep, we're getting covered by this part of the graph. We're getting covered here, and here, and here, and here, and here, and here. And if you look at that x value of 1 and you go, wait, is that x value going to get covered? It doesn't get covered by that pink function, but it does immediately get covered by my blue function. So I've got 0.999999999 getting covered, and as soon as I hit 1, I start getting covered by that other function. And we are covered all the way to infinity. All real numbers, or you can use the fancy R notation, or -infinity to +infinity. The range is gross. We're not going to talk about that. That's more of what we do in pre-calc, is talking about the range of these nasty things. But just so you know that is a common misconception with domain is it's not describing what the graph does or like the disjointedness of it. It's describing what x values map to something on that function. So I think that's kind of cool. Maybe you hated that. It's fine. Let's go ahead and take a breather, like stretch break. Everybody stand up and stretch. Stand up, stretch. We're going to take a quick break before we move on to the next problem.